Welcome back to Reconstructing Relativity. This is Chapter 8 called Synchronicity and Time Skewing. Now, I'm going to try something a little different today. My last video was a little bit scattered. I'm going to try to focus better on saying what I want to say by mostly reading from my book where my words are more carefully chosen. So hopefully that'll be more clear. And by the way, helps me out if you like and subscribe to the channel, and also put comments down and let me know how I'm doing, or if you have suggestions for how I can improve what I'm doing, or you have questions. Let me know. I'd appreciate that quite a bit. All right. And besides the readings, I'm going to put up a few graphics, and so before I get started, I'm going to bring back the graphics that I included at the end of my last video and tell you what they were, because I just kind of threw them in there randomly without any comment. These are 3 animations from our constructive model viewpoint. So this is from the viewpoint of space. Go back to the bug and the car model. If we're following along with a particle, this shows the oscillation of the energy within a particle. So with velocity over c equals 0, it's not moving through space. Harmonic, symmetric, but at a quarter of the speed of light, things become a little bit lopsided. At half the speed of light, definitely lopsided. We also see a shortening in the left to right direction, which is the direction of motion. So the stronger, you have to get up above half the speed of light before the relativistic effects really start to manifest themselves strongly. But this just gives this kind of 3 animations of different levels of relativistic effects. So we've seen from our constructive model so far, pretty obviously, how the time dilation occurs physically and how length contraction occurs physically to remain harmonious. The particles all have to get shorter in the direction of motion to maintain that harmony. But I mentioned that there's a third important piece of the relativity model. To get at this third important piece, we need to go back to the realm of philosophy for a little while. Einstein made a philosophical choice that was based on his values as a scientist, which resulted in the way he described relativity and ultimately the way all scientists since have described reality. Because scientists value measurements, they made a practical choice which has affected their interpretation of relativity and the way they explain it when they teach it to others. You may have noticed in my earlier discussions that I have assumed that space and energy simply exist, just as bugs and air simply exist. In my proposing the bug swarm model as a metaphor for trapped energy as particles of matter, I also simply assumed that time existed without further explanation. I also said that each particle had its own rate of time and suggested that any living beings living in a state of motion would not be able to tell that their own personal rate of time was slowed down relative to some other standard. Everything would seem normal to anyone enclosed in a spaceship traveling at a very high speed, and neither the time rate nor the length changes would be visible or detectable in any way within that environment. You might now be saying, really? If a basketball was squashed into a spheroid, would I not see that? But if you carefully consider the fact that your eyeball and the lens within would also be flattened in the same proportion in the same direction, and your arms and fingers would also be shortened in the direction of motion, the basketball would look and feel perfectly round to you in your moving world. It is this very fact that temporal and dimensional changes would be unperceivable to moving observers which led Einstein to abandon the notions of absolute space and absolute time. For him, since it was impossible to measure one's own time rate and length measurements against an absolute standard, he disregarded the concept of an absolute standard. The observer living on a planet in a solar system in a galaxy cannot escape from the reality that he must be moving, yet he cannot measure his rate of motion through space by any objective measurements of time and length in his moving reference frame. This was the lesson learned from the famous Michelson-Morley experiment. So I've talked about, the Michelson-Morley experiment, what they expected and what happened. And what they did not understand was that on the micro scale, the experimental apparatus, being composed of particles and atomic structures, which were trapped forms of energy traveling at the speed of light through space, would be assuming slightly non-spherical shapes. The effect of this was an unperceivable shortening of the apparatus in the direction of motion, so that the two light beams in the macro scale experiment would always complete their round trips at the same time. This is important. This shortening was not unperceivable because it was very small. It was unperceivable because every physical measuring device would shrink in the same direction by the same ratio. Their instrument was in fact sensitive enough to measure the tiny time differences that would result in this experiment due to the speed of Earth around the Sun. But they implicitly assumed that the apparatus was rigidly composed of hard little nuggets of stuff that would not deform in this way, as we've been describing, due to the speed of the apparatus through space. From this and many other experiments, it was repeatedly demonstrated that measurement of the speed of the Earth through space was not possible in a laboratory. But when Lorentz attempted to explain physically why such a measurement was not possible, his ideas were rejected. Lorentz said that the length of the apparatus must be shrinking by the factor gamma, but he had no reason why that should be so, other than it must just be so for Michelson and Morley to get the null result that they did. Since Lorentz did not have the perspective which we now have that structures made of particles are composed of energy which also travels at the speed of light, Lorentz's explanation seemed contrived only to match the experimental results. He had no convincing physical reason why the measuring apparatus, assumed to be composed of solid nuggets of matter, should be deformed by this amount. However, since the clocks that measured this round-trip time were also moving through space with the measuring equipment, and the clocks were also constructed of subatomic particles which experienced the same slowdown from their motion through space at the same speed, the laboratory measurements of round-trip times for light always produced the same numerical results. The round-trip speed of light was always measured to be the same. But Einstein took it one step further. He said that the one-way speed of light is always the same, regardless of the speed of the apparatus that measures it. That's quite a statement. Look again at the horizontal bug swarm plots that show a harmonious return of all the bugs at the same time. It's quite clear that in those graphics with v greater than 0, that some bugs spent much more time moving in one direction than they did after they turned around. Isn't the bug that is moving to the right when the pattern is moving to the right, moving at c minus v relative to the pattern center? And isn't the bug moving to the left when the pattern is moving to the right, moving at v plus c relative to the pattern center? Although the round-trip average speed is the same, wouldn't the one-way speeds as measured in the moving frame be quite different? How is this reconciled with Einstein's statement that the one-way speed of light is always measured to be the same? The answer is time skewing, and this concept is central to all that will follow. For the moment, let's follow Einstein's logic and consider the practical aspects of experimental measurements. Remember that Einstein's statement is that the one-way speed of light is always measured to be the same. Remember also that measurement is the primary scientific value. Einstein says that if you want to measure the speed of something, you need to have two clocks in different places that are synchronized. That is, they must not only run at the same rate, but they also must read the same time at the same time. What does that mean? And how is that accomplished in practical terms? There are several ways to do it. You might place two clocks side by side, set them up to the same time, and then separate them by moving one clock to a different location. This method seems simple and straightforward, but in fact there are some very subtle aspects to it that need to be discussed in detail. We will come back to this method of synchronizing separated clocks later. The second way which clocks that are separated in space can be synchronized is considered the standard Einstein clock synchronization procedure. It also seems rather practical and reasonable, but when viewed in light of our constructive model, I think you will see that this method also contains a boatload of irony. Einstein's method of clock synchronization is as follows. Two clocks are tested to verify that they run at the same rate. Then the clocks are spatially separated. One clock is at station A and the other clock station B. To synchronize the clocks with Einstein's method, at a specific recorded time on clock A, station A sends a signal, a light signal or radio signal, to the clock at station B. When station B receives the signal, it records the time on its clock, and it also immediately sends a return signal back to A. Station A records the time when the return signal is received. Next, station A and B communicate with each other about the recorded times. Clock A has recorded 2 times. Clock A and clock B are said to be synchronized by Einstein's method if the time recorded by clock B is exactly midway between the 2 times recorded by clock A. Now the irony should be apparent. Because the light signal or radio signal, which also travels at the speed of light, is used to synchronize clocks in this way, if 2 clocks synchronized in this way are then used to measure the speed of light between A and B, the one-way speed of light will always automatically be guaranteed to be the same numerical value in both directions. Now, the fact that the two-way speed of light is the same in all directions is a rather remarkable fact which occurs, as we have seen, because the structures of measuring instruments, including rods and clocks, are composed themselves of energy which must play by the same rules as the light being measured. The assertion by Einstein that the one-way speed of light is the same in all directions was a bold move indeed. The first time I heard it, it made me laugh. I thought, well, yeah, of course, if you synchronize your clock that way, that's the result you're going to get. But we'll come to see how he made this argument convincing, and we'll see that what I'm calling time skewing is exactly the correction required to make the one-way speed identical to the two-way speed. Now, this gets really interesting. Follow me on this. You remember from our gamma equals 2 picture of the bug swarm or the energy swarm inside of radial motion inside a particle, that when we track the bug moving to the right, energy moving to the right, we had a total of 30 steps, and it took 28 steps. There were 5 colors, 6 steps each, a total of 30 steps to do the round trip. And you can see that it took 28 steps for the bug moving to the right to get out to the border, and then just 2 steps to get back. You can see that in the picture at the left. Just 1, 2 jumps back, but 28 time periods to get to the right. So if the macro equals the micro, we can use this picture to also look at this idea of synchronized clocks. Suppose someone at A wants to synchronize a clock with someone at B. We go from micro inside a particle to macro inside a spaceship, or 2 people that are at remote locations and they want to synchronize their clocks. And suppose they happen to be going to the right at 0.866 C, which gives them a gamma of 2. Well, in the universe time frame, we know that it takes 28 of the 30 time sectors for the light to go from A to B, and only 2 to go from B to A. But to synchronize these clocks, B is supposed to set his clock midway between A start and A end. So A sends a signal at 0, obviously the signal gets back at 30 ticks. Whatever B's clock says when it gets there, maybe B's clock says just 28 when the signal gets to it. Well, that's not synchronized. It should be reading 15. So if B was initially reading 28 and had to reset it to be 15 to be synchronized, it would have to set its clock back 13 ticks. That's the offset between what we know from the constructive model point of view of being still in space, that it took 28 time periods, but B needs to set its clock to say 15 in order to be synchronized with A, according to Einstein's rule. So B needs to set its clock back 13 ticks. Are clocks A and B synchronized? Well, according to Einstein, yes. According to Einstein, we'll see that's the practical thing to do. But from the constructive model point of view of the state of the universe, what we would actually say is, well, no, when A sent its signal at time 0 in its clock, B was reading minus 13. And then by the time A's clock got to be 28, B was reading 15. And then at that point, A's clock was reading 28. And then the signal got back at A's time 30. And so they appeared synchronized, but were the two clocks reading the same time at the same time? In the state of the universe, no. They were reading different times at the same time in the state of the universe. And we'll talk about the state of the universe perspective. But that's the thing about the synchronization. There's a synchronization that works, that's practical, and that fits relativity as it's written. But behind the scenes, if we look at what's really going on, we see that there's an offset in time. And this is what I'm calling time skewing. Now, relativity doesn't refer to time skewing because, as far as they're concerned, A and B's clocks are synchronized. There's no offset, no issue there. That's why you never hear about that. But from this point of view of knowing what's actually going on, you could say that clocks that are ahead in terms of position, in terms of motion, have to set their clocks backwards in time in order to be synchronized. Speaking of time, this video is running longer than I wanted, but before we go, check this out quickly, and this is where we'll start next time. At a V over C of 0.866, which gives us the gamma of 2, which we were just looking at, the offset between what we see as the universal turnaround time of 28 and the synchronized turnaround time of 15 is 28 minus 15 is 13. And here's the punchline. 13 over 15 is 0.866. That offset is equal to V over C. And that's not a coincidence. That's how it works. That's how this works. It works for all the V over C ratios. This is the reality of how this equation works. And so we'll explore this a lot more later. Just wanted to drop that and catch you on the next page on the outro page. Thanks for watching. We'll pick up on this topic and keep going with it in the next video. Please like, subscribe, share this video, and find my book on Amazon if you're so inclined. And feel free to leave a comment or a question. I'll get back to you. Now for a little outro tune by Amy Mann. Wonderful lyrics in this bridge. The song's called I've Had It. See you next time.
And before you know that it's free, you've had it. You've had it. Like most amazing things, it's easy to miss and easy to mistake. For when things are really great, just means everything's in its place.